Good. Thanks to everybody for coming back. Theo is going to give us a talk on irreversible features of Euler.
Good, thank you very much for the invitation. Right, so I'm going to talk about some joint work with Tarek El-Gindi and Andrew John. Okay, so I'll just begin with a discussion of the 2D Euler equations. So therefore, velocity vector field U, which is divergence free, and tangent to the boundaries. And so I'm thinking of a setting. Actually, for most of this talk, I'm going to be talking about annular domains, so region between two concentric loops. Fluids occupying the shaded region and is tangent to the boundaries of the domains. Okay, so in 2 dimensions, there are sort of 2 structural simplifications that happen. One is that any divergence-free velocity field can be written as the skew gradient of some scalar function on the domain, the stream function, that is some sort of Hamiltonian of the velocity field. And the significance of this representation is that if you look at level curves at any given instant of time, level curves of the level sets of the stream function, and the velocity is just tangent to them. Hence the name streamlines of the stream function. Okay. Then there's a dynamical simplification that if you look at the right sort of variables, this equation simplifies conceptually. And of course, everybody here knows this. So if you look at the vorticity, the skew divergence of the velocity is just a scalar function in 2D. Then the vorticity field is transported as a scalar. The velocity is recovered by non-local Biot-Savart law. Okay. So what do we know about this equation? Well, it's classical that if you're given, say, initial data, which is in C alpha, for instance, then you have a global solution in C alpha. But if you measure the solution in C alpha, then in principle, this thing can grow double exponentially. So C alpha is a good base space for the equation, except that at infinite time, you leave it. And leaving C alpha at infinite time is nothing but sort of physical procedure of Euler. So in view of this equation, if you start with some blob of vorticity at the initial time, it's just transported by the divergence-free drift. So it's some area-preserving rearrangement, which over time can develop tendrils that are very thin. Such thin tendrils correspond to growth of gradients of that dye of the vorticity. And so you would expect generically, in fact, to leave C alpha at infinite time. On the other hand, Udovich proved the following while posing this result, which is if you just take vorticity in L infinity, then for all time, there's a unique resolution of this equation, which stays in L infinity. In fact, because of the structure of this transport equation, you have that the norm is a constant in time. So with this space, say you could introduce a unit ball of vorticity functions in L infinity. The Euler equation forms a nice dynamical system that in fact is compact in the right topology. So if you look, first of all, at finite times, let ST be the solution operator for Euler. If you flow this ball, you actually get the ball itself for all time positive or whatever negative, doesn't matter. The ball itself, because the system is reversible, so you can get from any point in the ball some data that gives it to you at any given time. So you have a perfect map from this set to itself. And if you endow this with the weak star topology, the Euler system is compact at emphasis. Why? Just because you have this uniform bound on the L infinity norm, so you're guaranteed that at least along subsequences, you converge weak star to some limit points. And those limit points, as we've discussed at length in this conference, must have L2 norm, which is lesser than the initial data. Okay. I mean, lesser or equal. For any of them. So you, in principle, you could think of at finite time when there's sort of winding around on the surface of this ball, and then at infinite time it can jump inside. Okay. So that motivates formalizing the study of the long time behavior by thinking about the limit set of this entire phase space. So that would just be the union over all omega zero, which are in that ball, and you look at the weak star closure of the orbit at the point. So you just union over all possible weak limits starting from any data in that set. And this could be called sort of the real attractor for 2D orbit. This concept, as far as I know it, was sort of written about by Cheryl.
It's not a global attractor in the classical sense.
No.
The union of the-
Yeah, it's not, but it's a reasonable object. So if you do the classical sense, you get the ball itself, which sort of carries no information. Because if you allow to take limits of data, then that's not interesting. I mean, so the interesting thing is like, what are all the possible weak limits? And the point is that this set here, I mean, elements of this set are what you might see if you do a very long time simulation of the system. So, what? But trajectory by trajectory.
You should call that system.
Per system. And so the point is, what do you see? So if you do like simulation on, say, the two torus, you just put random data. Then over the course of time, what appears to be a robust feature of the system is that you organize into some coherent structures, maybe a couple of vortices, a couple of satellites. Nobody really knows. But the main point is that the generic initial inputs give rise to very specific outputs. So Sherman has a conjecture about the content of this set. So conjecture about the makeup of the attractor, which I'll come to at the end. It's a sort of very beautiful conjecture, but we can sort of come back to it. The basic question that we'd like to answer is, why should there be any sort of reduction in the complexity that you see when you observe the system? And why should it be that over a long time you don't recurrently get things that look essentially like random fields? Why do they always have this kind of special structure? Okay, so what do we actually know about the long time behavior of the Euler equations? What are the existing results? So they're not very many. So prior analogy. One of the first really, so aside from the existence theory, of course, fundamental, one of the most important contributions was by Arnold, in which he identifies a class of stationary states which are stable in L2 of vorticity. So these are Lyapunov stable steady states. This is formally infinite dimensional Hamiltonian system, Euler. There's no sort of obvious sense in which things can be asymptotic attractors. There's sort of non-obvious sense that we'll talk about shortly. But these things, at least Arnold identifies huge families of steady configurations that remain in a coarse-grained sense there. You slightly perturb them. So these equilibria, I mean, it makes sense if you want to understand the long-term behavior to begin an investigation around stable equilibrium. You expect to be able to say more. Okay. So there are some results near equilibrium. One of them, by Nadesh, in which he proves wandering in the L infinity topology. So notice, it's actually an important point that this topology here, L2, is not the same one that we have the dynamical system in. It's weaker than L infinity. And what Nadesh really showed is that so sort of contrary to finite dimensional intuition, there's a point and a neighborhood around that point, such that if you start Euler from any point in this neighborhood, there's a time at which all those trajectories forever leave that neighborhood. They never come back to that area of phase space. And so in a way, you can think of this as like a non-ergodicity. At least there's no dense orbit in the strong topology of L infinity. His example, in fact, can be, well, you can say more about it. You can say that he gives an example of an initial data, omega 0, such that if you look at the resulting solution starting from omega 0, measured in C alpha, it grows like t to the alpha. So this is related back to this point about leaving the C alpha phase space at infinite time. He gives one of the first examples of infinite time growth and loss of smoothness in C alpha. So some kind of filamentation is happening, and it's associated to his wandering point there. So then there's a host of results on loss of smoothness, like this last statement. So loss of smoothness. This is due, for example, to Theodore himself. Then there's work of Kiselev, Schwerek, Denisov, Shulatosh, and many others, in fact, which give examples of infinite time growth of solutions with Euler. Generally speaking, aside from those of Yudovich himself, which assume some special character of the solution near the boundary, generally speaking, these constructions, the solutions investigated, are not stable to general perturbations. They're chosen in a particular way. And so you wouldn't expect necessarily this to make statements about generic behavior. But all of them share the feature that they're close to some stable state. So either on the torus with symmetry or on the disk. This result, of course, as people here know, establishes the sharpness of this upper bound. So in fact, what comes from the PDE theory is sharp. So I'll say examples, but not necessarily robust. Now there is a transient statement which is robust, and that's a theorem of the Koch that says that any steady state whatsoever, stable, unstable, doesn't matter, is stable, unstable in L2, is nonlinearly unstable in C alpha. So any steady has the property that there exists. So let's call that omega bar. Has the property that there exists an omega 0 such that for any epsilon, there exists an omega 0 such that you're close by epsilon and C alpha at time 0, but there is some time t, capital T, let's say, such that you're far in C alpha by m, and epsilon and m are arbitrary. So you can sort of transiently make things as filamented as you like, but then after this time t that Koch gives, it's not clear what happens to that solution. So in a way, it's on one hand, it's more robust, more generic, but on the other hand, it's not an all-time state. And finally, there's this result by Bedrosian and Masmoudi, which, in a sense, establishes this picture in a very special area of the phase space. So what it does is it studies, and there's follow-up works to this, given a Lyapunov stable equilibrium, in their case, Colette flow, so just linear shear flow, you take any perturbation sufficiently close and sufficiently strong topology to that shear flow. Then they prove that these weak limits exist. They are themselves shear flows, so you converge back to equilibrium, slightly modified from the thing you started close to. And to get there, you strictly mix. So for the purpose of this talk, by strict mixing, I simply mean that, say, the L2 norm is strictly bigger than, the L2 norm of the data is strictly bigger than the L2 norm of the weak limit. Okay. So Bedrosian and Masmoudi established mixing and then disadvantage. So convergence back to equilibrium. And it's this type of result that I think sheds some light on the conjecture of Schnirelmann, which is, well, maybe it's time to say what that is. So Schnirelmann's conjecture is that this set, the omega limit set, or the persister, is sparse, and it consists exactly of trajectories of the Euler equation, which are precompact in L2. Namely, it's all those initial data, such that if you flow Euler from the initial data, you do not mix at infinite time. Examples being steady states, of course, and time periodic things and so on. So he's saying whatever doesn't mix, that's whatever you see. Okay. And in Bedrosian Masmoudi case, that's precisely what happens. Everything except a very sparse set of data mixes, and you go to that sparse set of things. Okay. So mixing is a mechanism for information loss, obviously. Mixing is something that happens in the Eulerian space. I mean, the observation, the L2 norm of vorticity decreases. This is an Eulerian measurement, so something to do with the velocity vector, the norm of its curl. But there's a dual description, which is implicit in when you think about mixing, and it's been discussed a lot at this conference, which is Lagrangian. So the Euler equations have an equivalent Lagrange formulation, which was first really elucidated by Arnold. So by Lagrange, first of all, I mean the flow map, or the location of the particles within the Euler solution. So physically, what is the state of the fluid? And then it turns out that you can think of Euler solutions as being, well, living, first of all, in some configuration space. Just like this is volume preserving diffeomorphisms. Let's say this annulus, starting at the identity element. All the Eulerian stuff is happening up here in the tangent space. So here's the motion of the vector field. But then down here is some isotopy in the group of diffeomorphisms. Your state of the fluid is connected to the identity by some path. Arnold showed that this path is actually geodesic for a certain with a certain metric, the L2 metric, on the group of diffeomorphisms. So he introduced distance between, say, phi and the identity, L2, which is you infimize over all paths in the group, connecting the identity at time 0 to your state phi at time 1. And you just integrate the kinetic energy in that path. And so extreme points of this, given two states, two diffeomorphisms, extremizers are exactly Euler things. Why is this connected to that? Well, it turns out that there's something very special about the group of volume-preserving diffeomorphisms in 2 dimensions versus other dimensions. So the thing that's special is that if you use this notion of distance, then the diameter of this group is actually infinite. This is the result of Euler. So the diameter, this is infinite, namely that there exists a sequence of diffeomorphisms by n, such that you can get to arbitrarily large distance by going along with the sequence. Namely, you can't find some shorter path that does it in finite length along for the sequence of diffeomorphisms. And this result is, by the way, false in higher dimensions. So if you go to 3 dimensions, suddenly the diameter is fine. That was a result proved by Stony. And so the content of this is that the configuration space is sort of can hold. So thinking of diffeomorphism, which is far from the identity in this sense, it has to be sufficiently complex. As we're going to see, it has to do with sort of the twisting and winding of the diffeomorphism. In fact, Eliashberg and Ratu's proof uses nothing but time-1 maps generated by little radial vortices. You can show when you twist up space with a little radial vortex, the distance gets ever longer. So the configuration space has an infinite capacity to absorb complexity that's being reduced in the tangent space. So when you do this mixing, you're simplifying the coarse-grained picture of the flow. But that simplification has this dual side, which is that if you actually look at the state of the fluid, it's going to become increasingly complicated. This is like a reservoir for the complexity. That's sort of the view that we'll take. Okay, so now I'll tell you what we proved. So nearby any Arnold state, or just which is called stable, L2 stable, steady state on any angular domain. The following things hold. So okay, so one, solutions such that the C alpha norm grows essentially like T to the alpha. So these solutions are dense in the C alpha neighborhood. Of any such point. So you have your steady state of like a bar, you have some C alpha neighborhood, then there's a dense set of points in here which experience indefinite gradient growth. So there's a sort of filamentation. I should say that I forgot to mention this, but Udovich, who established some of the first results on this, also conjectured that filamentation should be generic periods. You just take any old data, and it should be that the solution blows up in C alpha. So this is sort of like a modest step towards that, just by saying that if you're at least nearby stable equilibria, that's true. Is what you would expect. But so moreover, you can find examples where the gradient growth, even in L1, is like T. So this example. This. There are wandering neighborhoods. Namely, neighborhoods U with the property that if you intersect, this is an L infinity. So if you intersect U with the flow of U by Euler, this is the empty set after some T star, let's say. So you really take the whole open set of data, you flow it, and you look to see if it intersects with the original set. And after some time, it doesn't. This is like a version of non-rationally stated that's a bit stronger in the steady state table 1. All solutions, again, nearby. So, by the way, nearby is generally always going to mean in an L2 set, unless otherwise specified. So, any such solution starting nearby a stable steady state have the property that the Lagrangian flow becomes infinitely complex in the sense that the distance of the flow map to the identity grows at least like a constant times time. So it's really getting far in this configuration space. Moreover, it has gradient growth in L1 that's at least linear. And finally, there exists patches, vortex patches, whose perimeter grows at least like T. Any question so far?
I was expecting lots of figures.
Yeah.
They go much faster than me.
Well, I don't know. I mean, if you put like, if you have a circular patch, its velocity field is radial. You put a filament, passively, this is going to grow like T. Passive. So we don't do better than what you would get for a passive. I mean, our lower boundary is essentially what you would get for a passive.
Right, but if you have like crisscross improvement, I would expect it to grow.
Maybe, I mean, it's just always improved. So very well could be. I think the bound for the perimeter growth is double exponential. Probably have anything in between. Probably there's a case of linear.
Few concentric circles.
Yeah, for example, I mean, could be, they don't have to be active. Topologically and channel, also an example, periodic channel. It's like a cylinder. In fact, I'm gonna show you how this works now, just in the case of shear flows, this stable shear flows on the channel, the periodic channel. So what's underlying these results? It's actually a very simple statement about stability of twisting of Hamiltonian flows. So let's think of our domain as that. So here's our domain, but I'm also going to introduce this concept of the universal cover. So our domain M may be like torus cross -1. The cover, this whole thing is just R plus -1. So just period of. And if I have some shear profile here, so autonomous shear flow, then I know if I look in some small neighborhood where the velocity is like 1, if I look at a box like a mass of particles here, then this mass is going to travel at speed 1. So it's going to, at time t, it's going to be t away on the cover. So we always implicitly use the cover because when we write down the flow map for, say, any one of these shear flows like Couette, we have x plus t of y. This phi1 component is actually the location of the flow on the cover of the domain. You have to project, you have to mod by 2 pi to go back to the. And of course, over here, it's going to be at like -t. Now, the fact that these two masses get far away from each other on the cover, that's exactly related to these points about the distance and the gradient growth. So it's easy to see that if you have two masses of particles that become ever farther on the cover, then the gradient of the resulting flow map will blow up in L1. And moreover, the distance in this geometric sense that Arnold first said also is lower bounded by the distance of these masses on the cover. So what we need to establish, or what we establish, is that this picture, namely if you have a masses going in different directions, this is like a stable picture if you perturb the velocity field by something small, actually even in L1. So the statement is if you have a shear flow V of y equals 0, and you take any non-autonomous perturbation in L1. So I just perturb in any possible way. Then the picture of the flow on the cover is basically the same as it is for the autonomous shear flow. So having time dependence can't completely destroy the woundedness of the flow map around the cylinder. Now, why is this, at least it was a bit surprising to us at first? It's easy to come up with examples. By the way, I mean, it has to be written as the skew gradient of some smooth Hamiltonian function on the annulus. That's important. So it's easy to come up with examples, say on the torus. You can take sine of y, and then you can add just a little epsilon drift up. So sine of y from a 0 plus epsilon 0 from a 1. Now this perturbation is not of this type, because if you were to write the stream function formulation, stream function would be like the function x of the torus, which has the jumps as you go on the top of it. So it's not a smooth Hamiltonian function for us. But what happens with this velocity field is that the particle experiences for the same amount of time a drift this way and eventually a drift back this way. So that the whole flow map is just time periodic. So it cannot possibly be, if you admit those perturbations, that things like gradient growth and twisting are stable phenomena. It's easy to kill it. Yeah.
We have boundaries here.
Yeah.
So that perturbation doesn't satisfy a boundary.
Yeah. So I mean, this is on a different domain. Actually, some of the results apply to the torus, just we don't have stable steady states there. But even with boundaries, if you take a stream function, which is not periodic with respect to this period, but instead has some other period, you can come up with weird counterexamples there too. So it's really about having periodic, in this case, well, smooth function on your angular limit.
It's just the easiest one to.
How much time do that?
10 minutes.
Okay. Good. So why is this? So why is this true? It's actually a very kind of simple computation. You just consider the following quantity. So phi in this formula is interpreted as the lift to the cover. So this is the flow map on the universal cover, but you integrate it over the fundamental domain, the original annulus hat. And the point is that if you take F to be something that localizes you, say, to one of these regions, F can just kind of zoom in on some strip within the annulus. It's a function only of the second component of phi. Then this quantity measures what is the average horizontal location of particles which at time t occupy that particular strip. Okay, so it's telling you, if you look at that strip, doesn't matter where they came from initially, just where are they on the cover at time t. So we just look at the evolution of this quantity. There are two terms. So one term gives me U1 composed of phi times F. The other term is phi1 times U2 composed of phi times F prime. Okay. Now, this first term, both U1 and F, these are, so U1 in particular, it's a periodic function of X. F is independent. The periodic function. So now, even though this phi is on the cover, I can change variables. And I can just remove this area preserving if you want. Use X2, X1, X2. So that leaves that integral quantity invariant. Okay. I couldn't do that here because this, when I change variables, I get the image of the fundamental domain. But then x1 is not periodic function. So that's what happens here in this term. So this term is good. This term is good. And in particular, because I'm assuming that my velocity is close to shear flow, in particular, its U2 component is close to 0, and U1 is close to V. If I localize my F enough, this is basically V at some level, say Y1. I mean, that's roughly the contribution of this term. And that's exactly what's going to cause growth. So if I were to integrate this, I would get that this quantity is like T times that, which tells me it's close to wherever this box is. On the other hand, there's this other term, and it looks a bit scary at first. So this other term, you can change variables, and you have you get this integral over the image of the fundamental domain. So what is that going to look like? I mean, well, it's going to be some. So this is all contained in this cover. It's going to be some set like that. Maybe the diameter of the set is going to be like T or more. And so if you were to naively sort of estimate this, you might be worried that this x1, the horizontal location, is going to give you a factor of the diameter of this set. Set's getting really big in x1 diameter, so this in principle could be very large, and therefore the contribution of this term could be swamped by this one, which would be not stability. And it turns out that that doesn't happen, that this thing is also order epsilon. And the reason why is because of a topological effect. So we can, let's do a little more computation about it. So one thing is, because U is the skew gradient of the string function, U2 is D1 of some psi. And in fact, because we're close to the background, and the background is independent of x1, the shear flow, we just write it as the difference. And so this integral just becomes x1 times d1 of this difference being mean 0 on each. Well, okay, we can even choose this to be we can even choose it to be the horizontal average. So now this quantity is mean 0, and both of these things are going to be separately close to the thing for shear. And now this set phi t of m, we can also, we want to integrate by parts. We want to put the d1 derivative here. If we can do that, when it hits that term, it's all good, because now this is a periodic function on the cover, and so for the same argument here, you can change variables again. You just identify it with an integral over some fixed domain M, and it's close to the shear by our assumption. So this term will be small. The D1 derivative of the stream is going to be small. So that term is fine. The term that's tricky is the boundary term. Rewrite this. Let's just focus on that term. When we write it as a total derivative like that. Now, what is that boundary term? Well, you can write this image as a bunch of cuts. With the union of a bunch of cuts with horizontal lines. As an example, maybe the boundary of the fundamental domain after some time looks like this. So these two curves, because they're exactly 2 pi apart, have to always be 2 pi apart. I mean, it's a periodic vector field, so whatever it does to one boundary, it does to the other boundary. But you see that if you cut with a horizontal, so you can have disjoint intervals. In general, there'll be an odd number of intervals that make up each one of these sets. So this is going to be the union of some odd number of intervals, pi minus pi plus. P1 minus P1 plus, and so on. Now again, the distance can get arbitrarily long. I mean, the diameter here can get arbitrarily long. Just know that the boundary has to be a 2 pi translate of the other boundary, but the boundary itself can stretch out a lot. So in principle, if you're computing this, the boundary terms from integrating this total derivative at x1, you're going to have alternating things, but they're going to be far apart in principle. So you might get a term x1, and if it doesn't cancel with something else, then the boundary terms could be as big as the diameter of that crossing. And so exactly what happens is that, so there is a cancellation, and you can end up estimating this integral in terms of the dV norm of this psi. And the reason why it happens is because, well, the stream function takes the same value on both of these curves. If you write out what this integral is, you're just going to get the sum over those intervals of pi minus psi pi minus pi plus psi pi plus. You're going to get a sum of these sorts of terms. And the key point is this, for each intersection, there's a friend on the other boundary. So there's a corresponding intersection point with the other boundary. But the point is that they come at opposite ends of the interval. So this point is the translate of this point, but here it's the left end point of an interval, here it's the right end point of the interval. And it's for the simple reason that since there's an inside and an outside of this domain, like the Jordan curve, then you have to cross this boundary an odd number of times before you hit any point on the other boundary. So because of that parity, you always get a cancellation, and things that in principle are far end up just canceling their effect. And so in the end, you can rearrange these terms so that it's all like 2 pi, that's the distance between the boundary, times the sum of some alternating values of the stream function at different points. This alternating value, together with the fact that you can assume this is mean zero, allows you to control this. This is like directly dV, and then you can control the whole thing in terms of the L1 norm of the d1 derivative of psi. It's just one dimension. Okay. And so, all right. So if you sort of put that together, then it tells you that this quantity is roughly, without the dt, is roughly t times t plus epsilon t. And so the leading order behavior is to be in this box that's moving out with some fixed speed. If you have multiple speeds in your system, if it's like a non-trivial shear, non-constant shear, then there's other boxes moving in different directions. And so you can choose epsilon small enough to localize mass to an ever increasing distance, and thereby establish the. So maybe I'll leave it at that.